All right. Okay, so we've got a tetrahedral here for our electron geometry with 4 sets of electrons. Now, the bond angles, and bond angles here are a little more complicated as well. You can't really derive them as easily from a flat picture as we could for, say, the trigonal planar. So the bond angles here are 109.5 degrees. So you can kind of recognize, well, if I've got 4 things, they can't get as far apart as 3 things, so the angle's got to be smaller. But once you get into 3 dimensions, it's a little hard to just kind of do it on first principles like you can for a flat one. So that may be a little bit of information that's worth kind of memorizing or remembering there. Now, molecular geometry, we said, if they're all bonds, that is the same. So this would also be considered a tetrahedral shaped molecule, tetrahedral molecular geometry. Right? And we've seen an example here in methane. So 4 bonds, right? We know carbon likes to make 4 bonds. If you just attach a carbon to 4 hydrogens, you will get this shape. The carbons and the hydrogens carbon will be in the middle, hydrogens will end up at the corners of your tetrahedrally shaped molecule. Okay. All right, moving back to the other possibilities, right? If we have 4 sets of electrons, but 3 are bonds and 1 is a non-bonding pair, that would mean one of the bonds up here in this original picture are now replaced by a lone pair. But the other 3 are going to stay in about the same position. So I'm just going to choose the top one in my drawing as where I'm going to imagine the lone pair is now occupying space and repelling the other electrons. The molecule might look like that. So it's still tetrahedral in terms of the way we would describe where the electrons are, because there are still 4 sets of electrons spreading to the corners of what would be a tetrahedral shape. In fact, we can, let me just use a thinner pen here, right, and I'll use dashes, a dashed line to the tetrahedral shape being described by the electrons. But I'm going to contrast that to the shape of where the atoms actually are. So hopefully that's dark enough to come through okay on the video. So tetrahedral electron geometry, the angles here are still going to be about 109.5. It generally depends on what this atom in the middle is here. If it's a smaller atom, the lone pair will tend to occupy a little more space and push the other bonds away, maybe just a little bit more, and make the angles between the bonds a little less than 109. This is true of like water. The angle's about 105 degrees. We'll see water under the 2,2 actually. But if it's a big molecule, the bonds may be a little larger than 109.5 there. So but it's still going to be in the ballpark of 109.5 degrees. Now in this case, like we said before, what we're thinking now is we're trying to think about a shape that represents where the atoms are, but maybe not necessarily where all of the electrons are, since those electrons are technically located on a central atom. So I don't know how well you can see that in the video because the similar colors there of the pens that I'm using. But that's also a pyramid. But it's a little more squished. It's a squatter pyramid. The triangle that would be the base or the bottom hasn't changed from the original one, but the ones on the sides are now smaller. So this is a less symmetrical pyramid, but it's a pyramid with a triangular bottom. So we describe this shape as trigonal pyramidal. Right? It's a triangle-based pyramid. That distinguishes it from a tetrahedral because tetrahedral, all 4 sides are the same. Trigonal pyramid, the sides do not have to be the same. In fact, 3 of the sides are smaller than the 4th side there. Now, a good example here, right? We need a central atom that can make 3 bonds and have a lone pair. Well, nitrogen does that. You might be able to anticipate that from formal charges. NH3 or ammonia, we would have the nitrogen. We would have the 3 hydrogens attached to it, and there would be a non-bonding pair on the nitrogen, and that would adopt this trigonal pyramidal shape, right? Or be a trigonal pyramid if we're using the noun form. Okay, one more example for 4 sets of electrons is 2 and 2. So again, if I just build off that original picture, but I just keep 2 of them, and the other 2 would be lone pairs. So kind of lone pair there, and I'm using a little line here to represent where the lone pairs are. That is not how you would usually draw these. I'm doing that to be illustrative of the shape that is going on here in the picture. So usually, right, we just put those lone pairs next to the atom, but I'm trying to show how they're occupying the other positions in the tetrahedral shape. Again, with the kind of dashed figure of where the tetrahedral is based on the electron geometry here, right? The 2 of the electrons are still sort of occupying the corners of the tetrahedral in this VSEPR analysis. So electron geometry here is based on how many sets of electrons. As usual, this is a tetrahedral electron geometry. Angles here are still going to be about 109.5. Right? And like I said, with water, right, oxygen in the middle, that will be the example we use over here. It's actually about 105. So the lone pairs kind of push the bonds just slightly closer together than 109.5. But there's no way to really know that from kind of first principles looking at a structure. Now, in this case, right, we want to again think, well, where are the atoms? The atoms are there. Right, that's a boomerang again. So you might think, aha, here's the place we're going to use that really interesting term, boomerangular. It's not. Still hasn't caught on yet. This is also angular or bent. Either one is acceptable. And again, it's just kind of specifying there's 2 bonds here. They're not linear, not 180 degrees. They're at some other angle. It is important to recognize there are different angles that go along with the geometry we would describe as bent. The previous one was about 120. This one is about 109.5. So there are differences in molecules we describe as angular or describe as bent. And like I mentioned, water is the good example here. We have oxygen in the center. Right? We connect the 2 hydrogens, and we end up with 4 electrons or 2 pairs to go on the central atom. So that central atom has 4 sets of electrons, 2 bonding sets, 2 non-bonding sets, and that would fall into our angular geometry with 109.5 degree bond angles. The other thing probably worth pointing out, right, I'm trying to draw these to show the 3-dimensional structure. It's probably important to realize that you will likely not draw them like this, right? If you are doing the Lewis structure for water, and in fact we did this in the last chapter, right? When I originally drew it, I drew it like that. As you're drawing it, you may not realize what the geometry is yet, so you may well draw it linear. That's kind of the default of humans, is we'll draw things symmetrically if we can. But the important thing here is you should recognize that this isn't linear. Even though you drew or may have drawn the bonds as if they're 180 degrees, you should be able to look at this and go 1, 2, 3, 4. Right? Everybody, I'm pretty sure, can count up to 4. You should recognize that's 4 sets of electrons. That is not going to be linear. That is going to look like this structure back here, because those electrons will have an effect. Each set of electrons will have an effect on the other sets. Okay? Keep that in mind as we're going through. Okay, this was a bit of a short video, but I think 5 sets of electrons should just be its own video, so we'll stop there. We'll come back to address 5 sets of electrons in our structure.